Welcome to Physics 142 Online again. I'd like to work out an example problem using Gauss's law that comes right from your homework assignment. It's one of the problems on the homework assignment, and I won't be doing the entire problem, but the most interesting part is the one I'm going to do. So here's what it says. A non-conducting spherical shell of inner radius A and outer radius B has a charge plus Q uniformly distributed in it. Show that the electric field in the region A less than R less than B, so between A and B, is given by this expression, where R hat is a unit vector along the radius of the sphere. So this is what it looks like. You can see the sphere here is a shell, which means it's empty on the inside. So for distances less than A, it's empty. But between A and B, it's a solid that has a charge plus Q uniformly distributed throughout it. And so what we're trying to do is find the electric field in that region between A and B. So we won't really look at the answer that's given to us until we're finished and we're ready to compare our work. And the most important thing is to think about the symmetry. We're going to use Gauss's law, of course, to do this. We want to think about the symmetry and draw in the electric field lines. And it's pretty clear that this, being a spherical shell, has spherical symmetry. Since the charge plus Q is uniformly distributed throughout it, no matter what direction I look at the sphere from, whether it's the bottom or the top or the left or the right, or if I'm looking straight on, like the view is given to us right now, it looks exactly the same. And so the electric field lines, wherever there is an electric field, should be radially outward from the center, which is exactly what we have for the case of a sphere, or for that matter, for a point charge. So I'll just sketch in a few of the field lines. And knowing the geometry of the electric field lines, that helps us to figure out what sort of a Gaussian surface that we want to use. And indeed, it's not surprising that we'll choose a sphere. Now, where do we put our sphere? Well, the surface of the sphere is the place where we will actually evaluate Gauss's law. Right? Here's Gauss's law. The integral over a closed surface of E dot n hat dA is equal, of course, to the total charge enclosed over the constant epsilon 0. So where we put the sphere is we want its surface to be in the region where we're trying to find the electric field. So a sphere that has its surface between A and B is the one I want to use. And so I will draw a dotted line here to indicate the cross-section of the sphere whose radius is between A and B. So we will call that little r, that's the radial distance from the center to the surface of our Gaussian sphere. And if we're able to simplify the equation of Gauss's law, then we should be able to find the electric field on the surface of this sphere. All right, and we know the electric field is radially outward because of the spherical symmetry of the charge distribution. And for our Gaussian sphere, of course, since it's also centered on the center of the spherical shell, the n hat vector is always going to point radially outward as well. And that happens to be in the same direction as the electric field. That's one of the things about these problems when you have spherical symmetry that makes them easy to solve. So, since E is parallel to n hat on the surface, then we can right away write down what the dot product is. I'll just put a little arrow. E dot n hat is simply E, because it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle. Here the cosine of the angle is cosine 0 or 1. And n hat is a unit vector, so it simply has magnitude equal to 1. So E is all we have. This then becomes the integral of E dA equals Q enclosed over epsilon 0. And we'll figure the right-hand side out in a minute. But the next point is that E, because of the spherical symmetry, it shouldn't matter where we are on this Gaussian surface. Top, bottom, left, right, wherever it is, the magnitude of E should be constant on the surface. And of course, that doesn't mean it's constant everywhere, because if we're close to the center or if we're further away from the center, the value of E might be different. But at a particular value of R, then every point has the same symmetry as every other point. And so that means if E is constant on the surface, we can bring the E outside the integral. And so we get E integral dA, once again, and we'll rewrite the right-hand side. We've seen this in several example problems where the integral of dA means we add up all of the area elements over our Gaussian surface. Now, it's not over the surface of the shell, it's over the Gaussian surface. And the surface area of a sphere that has radius r is 4 pi r squared. So we have E times 4 pi r squared is equal to Q enclosed over epsilon 0. Now, what do we do about the Q enclosed? Well, here's the thing. If the charge is uniformly distributed throughout that volume, then we can solve for Q enclosed in the following way. We can write it down as the charge per unit volume, because this charge is smeared out throughout the volume of the shell. If we can find the charge per unit volume, right, and then multiply by the volume inside the Gaussian sphere that contains charge, volume inside the Gaussian sphere that has charge, then we'll be able to find the total charge enclosed by the Gaussian surface. And if you look at it, see, the Q is spread all throughout the shaded region, which is the thick part of the shell. Well, only part of that is inside the Gaussian surface. So here, if I do a little shading here, it's only this part that has the charge that we're looking for, right? It's the region between A and R. That's the part that actually has charge that's enclosed by the Gaussian sphere. Inside, for values of R less than A, it's empty, right? So even though that's inside the Gaussian sphere, there's no charge there. All right? So the volume inside the Gaussian sphere that has charge is actually the volume of what I've just shaded here. And that, if you think about it, it's the difference in volume between the entire Gaussian sphere and then the sphere that has radius A. So this term right here is 4/3 pi r cubed, which is the volume of the Gaussian sphere itself, including the central region, but then we want to subtract off 4/3 pi a cubed, because that is the volume of the region that has no charge in it. And the difference between those two is the shaded volume, within which there is charge, that's inside the Gaussian sphere. So all that's left for us to do is find the charge per unit volume within the shell. And that's not too difficult to do. The charge per unit volume is actually going to be, well, the charge per unit volume would be total charges Q, and now I want the volume of the shell. And it's actually got a fairly similar looking form to this. The volume of the shell is 4/3 pi b cubed minus 4/3 pi a cubed. And can you see why? That's the volume of the shaded region. So the volume of the entire shell, I mean the volume that goes all the way out to r equals b, that would be the 4/3 pi b cubed. But then we want to subtract off the 4/3 pi a cubed, which is the empty region at the center. And when we subtract those two, we get the volume of the shell. All right? So Q enclosed now I have as the product of two terms. The charge per unit volume in the shell and then the volume inside the Gaussian sphere that has that charge in it. And multiplying these two together gives us the Q enclosed. So we'll finish off in just a minute. We have E times 4 pi r squared equals Q enclosed over epsilon 0. So Q enclosed. Now I can simplify what I have here. It's Q over 4/3 pi times b cubed minus a cubed. Right, that's the first term. And then it multiplies 4/3 pi times r cubed minus a cubed. So Q enclosed, the 4/3 pi term cancels out because it's present in both the numerator and denominator, and we're left with Q times r cubed minus a cubed over b cubed minus a cubed. That's our Q enclosed. And as a result, we're ready to solve for E. So this means E is, it's simply Q enclosed over 4 pi r squared epsilon 0. Right? So it's this quantity. There's going to be a 1 over 4 pi r squared epsilon 0, and then just the Q enclosed term. So it's Q, might as well just put the Q here in the numerator, and then we've got r cubed minus a cubed over b cubed minus a cubed. Close the parentheses, and that gives me, as we always get from Gauss's law, Gauss's law only gives us the magnitude of the electric field. So we have found the electric field within the region between r equals a and b. This formula is valid anywhere between r equals a and b. If I just plug in a value for r, this gives me the electric field at that radius, at that distance. And so if I want to change this then to reflect the direction of the electric field, well, I know the direction is radially outward, and so I can put a vector sign on here, and I can put an r hat on here because r hat is the unit vector in the radial direction. So that's the direction that E points in. And we're basically done. Right? We see, oh, look at this. The answer that's given in the problem is missing the factor of epsilon 0. Okay, so that really should be up here. It was missing. I think we've got the correct answer now. So I hope this helps to illustrate how to use Gauss's law to find a problem, the answer to a problem that's not quite as trivial as some of the other ones that we've done involving things like point charges. This still has spherical symmetry, and so in some ways it's just like using Gauss's law to find the field of a point charge, but we get a more complicated result, and we have to really be careful. The part of this problem that's more difficult is calculating the Q enclosed. We have to really understand how we take the charge per unit volume and then multiply by the volume that contains the charge that we want, that's inside the Gaussian sphere. Okay, I'll see you in class.